All right, so this looks like this could be a good time to start now. Hello, everyone, and welcome to the Polariton chemistry webinars. We thank you for being here and joining us in this initiative to share our research within the community of molecular polaritons. Let me just give you a brief introduction of what this is about. So, as we are painfully aware now, the face of the world has changed. This little guy here had a very impact upon its arrival. And the scientific world was not exempt from its consequences. Most of us dread the memory of that fatigual February 28th, where they notified that the APS March meeting had been canceled, and it was just 2 days before it started. After that, most of the conference that we would have attended started canceling one after the other, up to the point where it was speculated whether any conferences were going to happen this year. However, well, this was just a call to adapt. The scientific world had to be able to ride the situation. And if anything, this was just a way to bring the way science is communicated into the 21st century. Fortunately, status of technology right now has made communications easier than ever before, and therefore sharing and being able to talk to one another across the world is just easier than ever in the history of humankind. Talking in particular about the polaritonics community, well, the University of California in San Diego is a very lucky institution in the sense that we have both a group of theorists and a group of experimentalists working on those topics. And we thought that it made sense to contribute to the field by trying to fill in the gap of interactions that scientists needed in this time. So we hope that in the same way that several other efforts have been happening to try to bring us together, these will also be successful, and we just hope that the venue that we're offering will actually help developing the knowledge in this field. So let me thank you again for being here. This is our lineup for the upcoming months. As you notice, we have people from all over the world. Well, if you're here, you already know what's the mechanics of the event. You just need to register in the link that we're providing. And please, we would appreciate if you were able to spread the word so that more people would eventually join. Now, let me tell you how this event is going to work. I'm about to introduce our guest speaker, and we want to actually take advantage of the features that this format allows us. So you all have the option of Q&A. So throughout the talk, you will be allowed to just type your questions, and you can also see what other people are typing. You can vote for the questions if you think they're relevant. At the end, I will bring those questions to the speaker so that he can address them. And also, if you have a very brief intervention during the talk, you're welcome to raise your hand in the chat, and I can enable your audio so that you can bring your question. If there is enough time at the end, you can also raise your hand once the speaker has addressed the questions in the Q&A option. I will give the instructions again once we're in that portion of the talk. So with that all settled in, let me introduce to you to our inaugural speaker. So we're very honored to have Jeffrey Owrutsky from the Naval Research Laboratory. He did his PhD in UC Berkeley on their Research Alkali on high resolution spectroscopy. Then he did a postdoc at the University of Pennsylvania, collaborating with Robin Hochstasser on ultrafast infrared spawn probe spectroscopy. And he was a postdoctoral fellow at the Naval Research Laboratory, working on femtosecond tunable deep UV photoionization. And finally, he was appointed research chemist at NRL, where he has continued and expanded his work on ultrafast nonlinear spectroscopy. And he's now head of the molecular dynamics section in the chemistry division. He has over 100 peer-reviewed papers and 2 chapters in books. And recently, he has been very prolific on topics such as dynamics of samples inside optical cavities, which is why we selected him as our inaugural speaker. So please give Jeff a warm welcome to your computers, wherever you're listening us. So Jeff, the mic and the screen are all yours.
Great. Thank you very much. I very much appreciate the honor of this introduction. Or you have to stop sharing, I think, for me to be able to share.
Sure.
And I hope wherever everybody is, I hope you're faring well through some of these times that seem sometimes challenging and in some ways quite bizarre. So I very much appreciate the opportunity to be able to kick off this webinar series that I appreciate Jorge and Joel and Wei to have put together for all of us. So this gives me the opportunity to describe some of the results that we have at NRL with my colleagues, Adam Dunkelberger, Andrea Grafton, a postdoc, and Blake Simpkins. where we've been looking at the dynamics of vibration cavity polaritons. So these vibration cavity polaritons come about as a result of strong coupling. And there's a rich tradition of looking at strong coupling in the optical physics community, especially looking at electronic transitions of materials such as quantum dots, quantum wells. And so one example is shown in the upper left. This is results from Lindsay looking at organic excitons coupling to a microcavity. These results were obtained in reflection, where here you can see the evidence of sort of the avoided crossing and the strong coupling that comes about as the cavity is tuned into resonance with the electronic absorption. And in these kinds of studies, it's also possible to look at things such as fluorescence as well as absorption. So these have also been used to look at new kinds of phases of matter, things like Bose-Einstein condensates, as well as polariton lasing. These typically started at low temperature, but then have graduated to being able to be observed at room temperature, which is clearly more convenient. So in addition to coupling to cavities, it's also possible to couple to different kinds of resonances. There's a lot of work looking at plasmonic coupling. This includes some of the recent work looking at very small picocavities, including single molecule strong coupling in some of these plasmonic resonators. And then in addition to that, in the course of looking at enhanced IR, the Hillenbrand group were able to see actually the onset of strong coupling. And this is probably a consequence of the fact that these phonon polaritons are relatively narrow. And so that really lends itself to getting into a strong coupling regime, because the phonon polariton width matches pretty well what the vibrational width is for the layer of organic material that they were looking at. So some of the kinds of strong coupling that we're really especially interested in the chemical physics community is being able to identify situations and examples and understand what happens when you can modify the chemistry. And so one of the groundbreaking experiments that demonstrated this capability came from the Ebbesen group, when they were able to show that isomerization of spiropyran was slowed down when it was put in a cavity. So compared to the results that they see outside the cavity, this spiropyran isomerization was occurred at a slower reaction as they were monitoring it over time. And so since then, there have been other people who've been able to see similar results. The Shigai group was able to see retarded, slowed down photooxidation. They were able to identify a situation in which it's desirable to be able to slow down an unwanted reaction. So this is something that they were able to see with J-aggregates on plasmonic coupling. So another case of looking at electronic coupling is one that sort of highlights one of the aspects of the strong coupled regime, which is you have coherent coupling, that you can have a lot of the members in an ensemble that contribute to give you basically a super absorption, like a super atom. And in this context, you have a lot of communication between these molecules. And this leads to something that was demonstrated by the Ebbesen group, that if you kind of slice up these molecules, they can have sort of long distance communication. This is something that's very exciting from a chemical perspective, because normally if you're going to have intermolecular interactions, the molecules have to be close together, but now you have an opportunity to do this at greater distances. And so all these I've talked about so far on this page have to do with electronic coupling. Another big breakthrough from the Ebbesen group was when they were able to demonstrate that with vibrational coupling, they could see a real impact on the reaction rate, slowing down for this the substitution reaction at the silicon group for this deep protection reaction. And so this is different because you're not really using optical excitation to be able to get access to the bright state. This is something that's actually happening in the dark. And so one of the things that's very exciting about this is that it's paving the way for an opportunity to be able to realize something that people have been trying to do for a long time. And this is to be able to do directed chemistry. Very soon after lasers were invented, people were very interested in being able to use them to do non-statistical mode-specific chemistry, where rather than just having the weakest bond break, if it's possible to excite a band that's primarily pumping energy in a specific bond, if people were hoping to be able to break a stronger bond. One of the things that sort of undermine that is that there's fast energy redistribution. So this makes this, generally speaking, something that's very difficult to do. So there have been strategies to be able to do controlled chemistry using coherent control, but another way to do that is to build in relaxation mechanisms, couple to resonances, and basically build in the kind of coupling that you can get the reactions to occur in a way that undermined your previous attempts to be able to do laser control. So one of the things that really was another very recent breakthrough is the report also from the Ebbesen group in the science paper, that they were not only able to change the rate of the reaction, but also the branching ratio. And so from a chemistry perspective, this is something that's very beneficial. When it comes to catalysis, really the name of the game is selectivity. And so one of the things that they were able to identify is that for a different kind of silicon, a different kind of molecule they synthesize that has two silicon atoms. This can get cleavage on the silicon carbon or silicon oxygen bond, and they found that they could change the branching ratio by coupling to several of the strong vibrations on this molecule. And so this not only decreased the rate at which this reaction occurred, but compared to what you see outside the cavity or off resonance, you can actually invert the branching ratio. And so this is something that was recognized by Joel and Stefan in this first reaction, that this is really exciting because it's an opportunity to really renew the interest in being able to do mode selective chemistry. And this now it's by doing optical cavities, by doing a Polariton chemistry. So I want to thank Joel because basically I grabbed this slide from his talk that I found on this molecular polaritonics website that actually is a nice compendium of a lot of talks as a result of a theory on molecular polaritonics meeting that was in Spain last year. So thanks, Joel. So this leads me to the outline for my talk today, in which I'm going to talk about the work we've done looking at molecular vibrations to be able to understand how the cavity coupling modifies energy transfer as a way to be able to get some insight how this coupling might be able to affect other kinds of processes, including reactions. So I'm going to start with a background on some of the basics, including etalons and strong coupling, briefly mention some of the frequency domain results that we've recently achieved at NRL, and then talk about the vibrational dynamics, including some of the cavity coupled tungsten hexacarbonyl, some recent saturable absorption results. But the stuff I really want to highlight are new results we have for coupling to a different solute, Nitroprusside, where we've done experiments that give us clear evidence of a polariton excited response. So in terms of cavity, strong coupling to cavities, as I mentioned, there's a long tradition of this going back at least to the 90s. And here in this figure, I'm demonstrating from this Tischler review that if you have a micro cavity at a particular wavelength with a certain width, and then you fill that cavity with some sort of material that has a matching resonance frequency and width with enough concentration that you can get a strong coherent interaction, then these hybridize such that you get a splitting that's called the Rabi splitting. And this is due to interaction that's similar to a dipole-dipole interaction that you get for pairs of dyes that are near each other that give rise to J-aggregates and H-aggregates, except in this case, it's the dipole coupling to the field of the cavity. And so this gives rise to these hybridized states that I will be calling the upper polariton for the one that's higher in frequency, and the lower polariton or LP for the one that's lower in frequency. And this Rabi splitting is dictated by both the concentration and the absorption strength of the material that's in the cavity. So I also wanted to make sure people understand sort of how these etalons work. I often get questions about how we do these experiments and how we construct the cavities. And sort of the simple answer for that is that we basically use the same kind of approach for doing experiments that aren't in cavities, where we have windows. Usually for us, these are calcium fluoride windows. But then we basically put mirror coatings on sort of the inside, either 10 to 20 nanometers of gold or dielectric mirrors. And so the way an etalon works is that you get a resonance when you have a integer number of half wavelengths, that's the cavity length. And some of the other nomenclature to be familiar with for these is that you have, if you have a cavity length that's has a number of different modes that's significantly longer than the half wavelength of the resonance, then the spacing between these modes is called the free spectral range. That's also inversely proportional to the path length in the index. And then the finesse is something that's related to the quality factor. And this is the ratio of the free spectral range to the width. And this finesse is really dictated by the reflectivity. So the higher reflectivity, the higher finesse. And so you can actually control the cavity resonance by changing reflectivity or changing the path length, where if we're getting strong coupling, this is going to be optimized where you can match the cavity width to the resonance width of the material. And so these cavities also can tune by angle tuning. Compared to normal incidence, they tune to the blue as you tune them, and this is a way that you can get the cavities into resonance with the absorption. So cavities are widely used in lasers. There's sort of one part of what you need, where the other one is a gain medium. And they're also used in cavity enhanced methods to get increased absorption. But it's good to recognize that a lot of those absorption techniques are used for concentrations that are very low. So you're on the other end of the spectrum, whereas for these strong coupling experiments, we're really trying to load them up with a lot of material. So as I mentioned, there's been a rich history of looking at electronic strong coupling, but vibrational strong coupling really has only appeared in the last 5 years. This was demonstrated first with the Ebbesen group, and very soon after that by my colleagues at NRL, Blake Simpkins and Jim Long. In both cases, they're coupling to carbonyl bands of polymer films, PVA for the Ebbesen group and PMMA at NRL. And these are first order cavities that are on the order of 2 microns. And you can see from some of our results that by angle tuning, we can identify what the Rabi splitting is. That's significantly larger than the width, so that we're in the strong coupling regime. So some of the other important breakthroughs and accomplishments that kind of lead to us being able to do dynamics and more complicated chemistry due to vibrational coupling in these cavities is some of the results from Ebbesen group, who demonstrated that you can extend these to liquids, and demonstrating them first with neat liquids, and that you can actually go to longer path lengths. And so that's very important for being able to do different kinds of solution chemistry and dynamics experiments. And it's also important to recognize that if you increase the path length but keep the concentration the same, you get the same coupling. So you don't pay a real penalty in the Rabi splitting for going to a longer path length, as long as you keep the concentration the same. And so that makes a lot of these experiments a lot easier to do. And so in work that we did at NRL, we demonstrated that you can also do this for dissolved species, demonstrating them for ions like thiocyanate in solvents, in addition to looking at the concentration dependence of the polymer. And here I show some of the initial work demonstrating that we can get strong coupling for tungsten hexacarbonyl in hexane. And as I mentioned before, the extent of this coupling depends upon the concentration times the absorption coefficient, and again, with the path length not included. So that actually puts me in a position to talk about some of the vibrational dynamics. But first, I want to take a quick detour and sort of highlight some of the recent frequency domain steady state results that we've gotten in NRL. This is work that's spearheaded by Blake Simpkins. And the first study is one in which we've carved up the material that's in the cavity into slices using spin-on glass spacers in addition to PMMA layers, and then positioned them in different places in the cavity to be able to trace out the field strength sort of within this first order mode of the cavity. And so what we were able to see that when you're near the edge of the mirror, the splitting is relatively small. When you're in the middle where you've got the peak field, the splitting ends up being quite high. And furthermore, you can demonstrate the cooperativity if we've got two patches that are symmetrically placed in the cavity, then we can see sort of the expected increase in the splitting. That should be on the order of a square root of 2. And so these are experiments that allow us to be able to identify the mode profile. And in some ways, these resemble some of the earlier experiments that had been done in the Ebbesen group, looking at emission from J-aggregates coupled in a cavity. So the other result I wanted to sort of mention very briefly is our being able to show that we can electrochemically modulate the strong coupling by having a cell that we've constructed that's connected to a reservoir that we can do electrochemistry in. So if we start out with benzoquinone that's got carbonyls that gives us strong coupling, what we can then do is do some electrochemistry, apply a potential. This results in reducing the carbonyls to dihydroxyquinone, which doesn't couple. And so here we can see the loss of the strong coupling. And furthermore, we're able to then look at some of the cycling characteristics. We're monitoring this also by looking at the index, which is a technique that's been used by other people to follow reactions in these cavities. And we find that as we increase the thickness, that it slows down sort of the cycle time for this reaction. So next I'm going to start talking about some of the results that we've done doing transient studies, looking at vibrational dynamics in these cavities.
Jeff, sorry, I have a question. So while you're here, sorry, can you go back 2 slides before? One more. Sorry.
No.
Yeah, I have a question about the mode profile. Yeah, this one. So, I mean, I understand that you are coupling with different intensities at different positions of the longitudinal length of the cavity. But how do you actually measure the different spectra if they are all within the same mirrors, pair of mirrors? I'm a bit confused about that.
Well, we're doing this, these are different iterations, right? So these are different devices. So one device,
okay.
I'm sorry if I didn't make that clear. So these are all different devices that have the absorbing layer positioned in different places within the cavity.
Okay, thank you.
So, so we've decided to start by looking at tungsten hexacarbonyl. This is really a poster child tune-up molecule for doing vibrational dynamics. It's got one strong absorption that's around 1983 in hexane, and it gives rise to ground state bleaches and excited state absorptions. If we pump, we get excited state population, actually not just in the B equals 1, but also the B equals 2. And so the characteristic spectra that we see outside the cavity are that we see a decreased absorption or a ground state bleach around where the fundamental is. And then we see excited state absorptions. In this case, we're up pumping to also the B equals 2. So we see 2 excited state absorptions, the 1 to 2 and 2 to 3. And so the vibrational dynamics have been measured by the NIST group, Ted Heilweil, back in the 80s. And you can find this in this annual review. And so these are our replicating sort of their results that demonstrates that we have V equals 1 relaxation time that's about 140 picoseconds, and then the V equals 2 is about 7. And so now we can use this molecule and see how it behaves in the cavity. And so this is work that we reported some years ago, Once again, this is what the IR spectra look like. And so these are some of the initial results that we got. This was actually before we got a camera. These are the equivalent results that are a little easier to look at that we've gotten subsequently that are consistent with what we measured before. And what we can see is what the predominant features are in these spectra. The one big absorption here is at 1968. And so we considered what the energy level scheme likely transitions would be. And it turns out that the transitions from either the UP or the LP to the V equals 2 don't really match what this absorption is. So this is where we realized that this big absorption is actually due to what we call the reservoir or the uncoupled 1 to 2 transition. So the other sort of feature of these spectra are best seen over here in the high frequency UP region. These derivative kind of line shapes are due to the fact that when you populate, when you pump population out of the ground state, one of the other consequences is that you reduce the coupling strength, and so these polaritons contract. Since we're looking at this in terms of absorption, the way this turns out is that it looks like you get a negative absorption or an increase where the polaritons are moving towards the center of the spectra, and an increased absorption out on the edge. And this gives a derivative kind of line shape. And so this also allows us to highlight some of the big differences when you're looking at transients in these polaritons. One thing is you're really restricted to the windows of where these polaritons transmit in terms of where you're going to see the spectra. And the other thing that's different is compared to outside the spectra, as I said with this contraction, these windows are kind of wiggling around as population relaxes over the course of the experiment. So the follow-up experiments that we did with tungsten hexacarbonyl was part of the fruitful collaboration that we've had with Wei and Hoel and their postdocs and students. And this is some of the first 2D IR. I think this is the first 2D IR of looking at strongly coupled vibrations. And we learned a lot of lessons from doing some of these experiments. One of them is that you have to keep track not only of the probe frequency in terms of the detuning, but also the pump frequency, since that's going to have a big impact on what you see. And one of the most important things that we saw is this is the pump axis here, and this is really at the frequency of the uncoupled absorption, what we're calling the reservoir, and we can see that there's significant signal there. And this demonstrates, even though you don't see much transmission, in the steady state, there's actually quite effective pumping at this reservoir frequency that you have to be attentive to. And as you'll see in a minute, in some of the work that we did with nitroprusside, we've taken advantage of the fact that you can use this reservoir pumping to be able to isolate the polariton response.
We have a question. Yeah.
Yes. Hello. So I'm Thomas Neumann from Harvard, from the group of Preneha Narang. And I would like to ask you a question actually about this scheme. Yeah, actually I have it here just on this slide. Before you were talking about this transient absorption, one slide back. Yeah, so it's the same scheme, right? So I would like to ask you about lifetimes, like if you are able to extract from this transient absorption the lifetime of the dark polaritons, and if you could compare it to the lifetimes of the bright polaritons.
Yes, so I'm going to get to the bright polaritons at the end when we do nitroprusside. And in terms of the dark polaritons, I'll get to those in just a second. And for the most part, what we see for the dark polaritons is that they have a lifetime that's the same as what we see outside the cavity.
Okay.
But as I'll show you in a minute, we've been able to isolate the response from the polaritons for nitroprusside, and it looks like it's relaxing faster than what we see for that vibration outside the cavity.
Thank you.
So as I mentioned, we got some very useful information and insights also about a lot of the interactions between the different polaritons from the 2D IR. In our lab, we then proceeded to do experiments that allowed us to isolate this polariton contraction more clearly. And one of the ways we did that was to be able to reduce the concentration by about a factor of 10 that then reduced the Rabi splitting by a factor of 3. The effect of that is that we were able to scooch the polaritons over to avoid these absorption bands and more clearly identify this polariton contraction. And so these are some of the results that we published a couple of years ago, that under these lower concentration conditions, we can clearly see at early times the polaritons are closer together, and then we can see that these recover. And again, this recovery time of the splitting is on the order of 140 picoseconds, which matches what we see outside the cavity. So that's also answering this way. And in other ways, we see that the reservoir very much resembles the dynamics that we see outside the cavity. But these experiments also allowed us to concentrate more clearly on what's happening in terms of the polariton contraction and observe that without sort of the complications of seeing the reservoir absorption.
Hi,
So one of the
Jeff,
other interesting things.
could I ask a question? This is Keith. Hi, how are you doing?
Hi.
Hi. Roughly what fraction of the molecules are you exciting to have this to induce this contraction?
That is answered more on this next slide or two.
All right, no, that's fine.
Initially, the concentrations were thought to be relatively low for some of the initial like pump probe tungsten hexacarbonyl studies. And we thought one of the reasons that we might get less efficient pumping is because one of the things that happens in the cavity is that you effectively can lose the excited state population as photons leaving the cavity, since the polaritons have mixed character. But as you can see with the slide I'm leading up to here, we found that for tungsten hexacarbonyl, we can increase the pump intensity so that we can really get complete contraction and coalescence of these polaritons to get it so that you only really see what looks like the cavity fringe by itself. And so initially we did this in a pump probe geometry, and then subsequently we realized that we can realize this just with a single pulse by looking at the self-modulation. So instead of being 2 pulses, this is just 1 pulse that we're monitoring the spectrum such that at low energy, low fluence, we can see the 2 polaritons. As we increase the fluence going to the blue, the polaritons come together and then they coalesce. And so we can actually see this saturable absorption effect. And so we've looked at this for this tungsten hexacarbonyl system, both outside the cavity and inside the cavity. Outside the cavity, really all you see is a decrease in this Lorentzian intensity. Inside the cavity, you see something that I think is a little more interesting because you see actually the spectral shape of this band change, going from seeing the polaritons to see it contract. You can see the splitting decreases with the increasing fluence. Similarly, you can look at the transmission that's at this uncoupled frequency that's initially low, and it's going to have the opposite behavior with the fluence. And so we've also, this saturation fluence is dependent upon the absorption coefficient. We've explored kind of what the cavity condition effects are and saturation conditions are in and outside the cavity. And some of the results are a little bit surprising to us. So it turns out the saturation fluence depends on the cavity length. Recall again that the splitting itself is independent of the length. And it also seems to have an effect on the absorption coefficient, which may be relevant to other kinds of processes that are mediated by absorption strengths in cavity. So with that, I want to really turn to the recent experiments we've done where we're trying to go beyond just looking at the contraction and reservoir absorption. Those are interesting, but they're not really polariton specific effects. So we've devised experiments recognizing.
Jeff, we have another
Jeff,
question.
hello, Jeff.
Yeah.
Am I audible?
Yes, Gina, please.
Yeah, I am Gina from ICER. I have a quick question about the molecule, just quickly to know. Like, this tungsten hexacarbonyl, this 6 carbonyl group, do you think all the carbonyl, the carbonyl in the axial and equatorial positions, they all contribute the same frequency, or you are considering as a complete Gaussian, so taking care of all these effects? I mean all the carbonyls together.
So this is a triply degenerate band, asymmetric stretch. So I would say all of the CO bands are involved in that normal mode, yes.
Oh, everything is inside the normal mode, okay, okay.
And I think as I tried to say, or I'm about to say, one of the kind of issues with tungsten hexacarbonyl is because it's degenerate, it has, it's able to actually have an anisotropy decay by exchanging kind of where the excitation is among those degenerate bands. And so that means that for tungsten hexacarbonyl, it can have a fast component to the polarization dependent absorption that's on the order of a couple picoseconds that can interfere with what we want to see in terms of the polariton dynamics. And so that's actually one of the reasons that we've gone to nitroprusside, which I'm going to talk about in a minute, because it's anisotropic, because it's non-degenerate, so it doesn't have any of this anisotropy confusion. And so,
thank you. I got it. Yeah.
Hey,
We
Jack.
have another question by Wayne Xiang.
Hey, Jack, this is Wei. I have a question about this saturation fluence that you talk about. You said that it's dependent on the cavity thickness. So I wonder, does it requires less? So what is dependence? You have less saturation fluence as you increase the cavity thickness, or the other way around?
I hope I can remember this right. Let's see. It's actually the saturation fluence is a little bit higher inside the cavity. And one of the things we found is that it gets higher even still as we go from 12 to 50 microns. And one of our colleagues has also done some simulations, and Igor Vergoffman's done some simulations, and it really looks like the cross-section seems to get smaller in the cavity. And so that could be because it's getting diluted by mixing with the cavity.
Oh, interesting. Okay, thank you.
As I was saying, we want to consider the different aspects of different solutes, the widths of the cavity and vibration, the anharmonicity relative to the Rabi splitting, because that's going to determine where the strong absorptions show up. Wei has actually done some work demonstrating that the shoulder that you see looks like it's probably a higher excited state absorption. I think they've also been doing some up-pumping experiments, but we've decided to look at nitroprusside, as I said, because it's non-degenerate and doesn't have this anisotropy problem. And we've used filtered pump and 2D IR. And so this is
we have another question by Keith.
Sorry?
Keith has another question.
Actually, I didn't raise my hand.
Oh.
But I do have a question about the unmixed absorption, if that's influenced by the fact that you've got the cavity filled so that there's some species near the mirrors and some near the antinodes.
Yep, distributed through the cavity.
If you had the sample only in a thin layer right at the antinode, would that largely eliminate the unmixed absorption?
Which unmixed absorption do you mean?
Where you showed that you had absorption into the upper and lower polariton branches, but also into uncoupled vibrational states that weren't shifted, that is, that didn't have the Rabi splitting.
I'm not sure. We haven't looked at that. That's a good question. If you can change sort of the contributions from dark states by changing where you are in the field distribution, right? Is that what you mean?
Yeah.
We haven't looked at that, but that's an interesting suggestion.
Okay.
So nitroprusside is basically NO substituted ferrocyanide. And so it's got a relatively strong NO band, around 1900 wave numbers. So our group looked at this like 15 years ago in connection with some of the other transient vibrational and rotational dynamics we did on some of these charged metal complexes. Since then, Munira Khalil's also followed up looking at both the vibrational dynamics as well as some interesting photochemistry that this molecule undergoes. And so here's just the out of cavity dynamics that we've also replicated that matches the results we got before. Again, we see a bleach and an absorption, and these decay times, in this case, they're considerably faster, on the order of 30 picoseconds for this population decay, T1, and close to 45 for this reorientation time, which is slow, so it's not going to get in our way. And so here I'm showing both what we see for the absorption out of the cavity, and then that we can get strong coupling. Under these circumstances, it's several hundred millimolar. That gives us about 40 wave number Rabi splitting. And so now we're in a position to do the selective pump and 2D IR. And so we are going to be doing both 2D IR and selective filtered pump probe. The filtered pumping 2D IR has been used before by Mike Fair or Ewing, and very recently, Wei has a paper, I think it's ASAP and ACS photonics, demonstrating this in vibration cavity transient studies. And so here, one of the things that we're going to take advantage of is that we can select the pumping, either a full spectrum LP or UP or the reservoir. So here's an example of sort of the UP spectrum that we're only going to pump one polariton. This has several advantages, suppressing oscillations, but it also really highlights that we're getting polariton specific responses. So here I can show you that if we have UP pump and look at the UP region, we see these big negative features that don't really show up for the LP pumping. And similarly, if we LP pump and look at this big negative feature on the LP side, we don't see it for the UP pumping. So this is sort of our first look at really clearly being able to identify that these are polariton specific responses. And so I can highlight this even more clearly by overlapping the spectra. The LP is the negative thing in red, LP pump, LP probe, UP pump, UP probe is in blue. Again, gives you a feature that's unique to those pumping conditions.
Jeff, I have a question. This is Joel. Sorry, so can you go back to the previous slide? Yeah, so here when you show this spectra on the right-hand side, so you describe this Rabi splitting contraction due to the bleaching of the molecules, but I just want to understand from Wei's experiments with you guys, there was also a short time effect where there was no Rabi splitting contraction at very short times. And do you guys see that in your in this batch of experiments? So we saw this like really large photon blockade, if you wish, and I was wondering, and we thought this was related to the degeneracy of the tungsten hexacarbonyl, and I was wondering if you see the same thing with nitroprusside.
I don't think we've really seen it, and I don't know that we've looked for it. I know you guys have been looking into the nonlinear optical properties. I think in the Science Advances paper, also looking at the concentration and length dependence, and we haven't really been looking for those effects, so I can't really say that we've seen them yet.
Yeah, Jeff, can you hear me?
Yeah.
Yeah, Adam, you go ahead.
Yeah, I think we looked a little bit for those just briefly, and for reasons we don't quite understand yet, that oscillatory photon blockade appears to be quite a bit smaller in this system.
Okay, which I think it coincides. It coincides with our hypothesis that it might be due to the degeneracy, but it will be interesting to chat about that. Yeah.
Definitely.
Yep.
Okay, sorry, Jeff.
No, thank you. So in addition to doing these filtered pump probe experiments, we've also been doing a 2D IR of nitroprusside in methanol. And so that's what I'm showing for the results here. The upper panel are 2D IR, again, plotted as the pump on the y-axis and probe on the bottom for 1 picosecond, 10 picoseconds, and 50 picoseconds. And then showing slices at the UP frequency in blue, and the LP in red, and then the reservoir cuts in black. And one of the things you can see from the 2D IR is right in this LP is that we see a little bit of tilting of this reservoir absorption at early times that then kind of levels out as you go to later time. And you can see that in the slices because you can see sort of the displaced nature of this LP pump that's indicative of the LP pump, LP probe polariton response that we're really trying to key in on. And so it's actually clearer to see this on the UP side because we don't have sort of the contamination from the reservoir absorption. So here you can see in the UP pump, again, we see this negative feature that subsides somewhat. And so this again is specifically a polariton response. And so this is something that we can isolate more effectively by looking at also the reservoir pump features. And so if we start in the middle here at late times, if we look at the LP pump in sort of the darker red and compare it to the lighter red is reservoir only scaled to kind of match what we see for the LP. And we see that there's a very good agreement with a little different scaling. We get very good agreement between the UP and the reservoir only. So this means that we've been able to isolate sort of the non-polariton response from the reservoir. And so then we can go back at early time and subtract it out and see the early time response. And when we subtract it out, we end up with the polariton only signal that again, we see this big polariton feature for the UP side, pumping with the UP, and the LP side pumping with the LP. And so we're working with Felipe Herrera and his colleagues using their multi-level quantum Rabi model to be able to come up with a theoretical description of these spectral features. And answering somebody's question before, so now that they're isolated, we can go look at the dynamics of these features and compared to the reservoir pump, which matches what we see, in this case it's for parallel outside the cavity. Now we can look at the dynamics here and we see that this has a fast component that may be a coherent response, but also an 8 picosecond decay. So that's significantly shorter than the 29 population time that we see outside of the cavity. And importantly, it's also longer than what we see for the dephasing time of the oscillations that's on the order of 2 picoseconds. So this looks like we've been able to isolate this polariton response and see a time that's intermediate between the outer cavity T1 and the dephasing of the polariton. So we can now extend this to similar kinds of results. This is tungsten hexachloride in chloroform, where in this case, it has a bandwidth that's similar to what we see for nitroprusside in methanol. And we see the same kinds of features. So this demonstrates that we see LP big negative signal, UP that doesn't show up in the other conditions. And it's demonstrating that these effects appear to be extend to other systems. So with that, I just wanted to take an opportunity to bring your attention to a JCP perspective that Felipe and I wrote that just came out a month or two ago. Basically, we recognize that getting an understanding of how these polaritons can translate into modifying chemistry in an understandable way will certainly benefit from collaborations between theorists and experimentalists, as well as good interactions from sort of the optical physics community that really understands the strong coupling well with chemical physicists who are really interested in using them to modify the chemistry. So with that, I'll just summarize to say that I've talked about some of the work that we've done looking at tungsten hexacarbonyl, including some recent saturable absorption results, and that we've brought these studies to a new solute, and we've been able to use different kinds of 2DIR and filtered pumping to demonstrate that we have an incoherent lifetime for this polariton that's shorter than we see outside the cavity. And we're hoping these studies can help understand how to use these to modify energy transfer and control chemistry. So with that, I want to acknowledge my colleagues for some of the steady state work. It was mostly Kenan, Wanmi, and Jeremy. Some of the NRL theorists include Tom Reinecke, One, and Igor Vergoffman. Acknowledge our UCSD collaborators, Wei and Joel, Bo, and Raphael, and also working with Felipe and his group in in Chile. And with that, I very much appreciate Jorge and Wei and Joel putting together this webinar series and giving me the honor of kicking it off.
Hello, Jeff.
Yes.
Hi, this is Gilad Aran. We haven't seen each other for quite a while. So I have a question about the shorter lifetime that you received when you measured the coupled levels. So can you say what is the source of the shortening? Is this just due to the actually to the line width of the cavity? Would you be able to modulate it by changing the quality factor of the cavity?
I'm not sure if that would be the case. I think that's something we can certainly try. So there are a lot of things that we can try. I don't think that we've even gotten to the point of trying serious detuning studies, which is another thing that we can do. But changing that cavity width is something else that we've thought about doing.
Because the decay time of the cavity might be involved in shortening the lifetime here.
That's true. That would be worthwhile to try and pursue.
Yeah.
It's nice to hear from you. It has been a long time.
Yeah.
Okay, we have another question from David Litzy.
Hello, hi, it's David Litzy from Sheffield. Really nice talk, very exciting, very interesting work. So kind of I work on putting excitonic materials into cavities and looking at kind of the interplay between excitons and polaritons. And in those systems, it's like the dynamics of the reservoir are actually critical to actually understanding the dynamics of the polaritons. And you get a process where kind of states in the reservoir can then feed into polaritonic states by various different scattering mechanisms. I wonder whether you'd thought about whether similar processes can operate here. I mean, do you think the reservoir is totally isolated from the polaritons, or is there some kind of interplay or interconnection between them?
I would think that, I did get a chance to cover some of the nice ultrafast work that you guys have done, and to sort of weigh in on the extent to which the results that you see are, we're going to be able to directly apply them to the stuff that we see. I know that some of the work that has been done, you can really directly see things feeding into the reservoir, and especially my limited understanding is that organic excitons really made it a lot easier than the inorganic in terms of the kinds of excitons to be able to use those strategies for modifying the dynamics. But we still have to think about whether, and we will think about whether we can apply them to these vibrational cases.
Sure. I mean, the other question, I guess, goes back to the one that you just had, I guess, previously. I mean, you're studying, I guess, the dynamics by a probe close to normal incidence, but you've got a great opportunity to essentially tune the fraction of the vibrational mode mixed into each of the polaritons. Have you ever done that, or are you planning to do that, or where do you think that?
Yes, we are definitely planning to do that.
Yeah. And does your photon mode interact with a single vibrational state, or will it, if you're coupling to your vibrational state at k equals 0, would your photon mode also be coupling to a different vibrational state at some large off-axis angle? So, I mean, you really studying pure systems, or are you actually mixing vibrational modes together?
I think we're sampling, in these cases, these are inhomogeneously broadened systems. And so I think to some extent, if my understanding of how this works is correct, you end up with mostly mixing homogeneous parts of the vibration. If I'm remembering Houdre's paper correctly, that you can get kind of a hole burning kind of effect. So I would think that tuning would change which sub ensemble within the heterogeneous distribution you're coupling to.
Okay. I mean, I meant if you had two vibrational modes which were fairly close in energy, whether you would actually be able to couple to both of them, or you couple to one at one angle and another one to at another angle. I don't know if you thought about doing that.
So there are people who've seen coupling to different modes, for sure. I think Randy Sparks has at least one paper, and let's see who. There are a couple papers, and that's a vibrational one. I know that there are some coupling to a couple different electronic transitions. So I think that's been demonstrated before.
Oh yeah, no, you can do that with different electronic transitions. I just wondered about vibrational transitions.
And I think you can also, I think in some of the Ebbesen strong coupling, that they were coupling to several modes, if I have that correctly, ultra strong coupling.
Okay, thanks very much. Thank you.
Before we go on, I would like everyone for being here. We had at some point over 200 participants. That was great. We had people from the UK, India, Israel. So that was great. I see that we have very interesting conversations happening in the chat. And I would like to give everyone a chance to ask, but unfortunately we're running out of time. So I'm just going to bring Jeff with one of the questions in the Q&A section. Okay, I'm just going to go with the first one. So why is there a symmetry in the upper polariton pump and lower polariton transient spectra for nitroprusside? Why does this asymmetry seem larger than that in the tungsten hexacarbonyl?
The symmetry?
The asymmetry, yes.
The asymmetry?
Yeah.
The asymmetry in the polaritons. That may be, do you mean here? Can you guys see my screen still?
Yeah, I think we can.
Is this the asymmetry in terms of the polaritons, or who asked that question?
Matthew do.
Matt, which asymmetry do you mean?
Let me enable his.
Hello, do you hear me?
Yeah.
Okay, hi. Thank you. So, so in the nitroprusside pump probe spectra, not in this one. If you go to the next slide. Okay, so yeah, that's the one. So if you notice when you have the UP pump, you see significant features both in the LP region and the UP region. But when you pump the LP, you only see significant features in the LP region, right? So I'm just wondering what the source of this asymmetry is. And it seems like you see something similar for the tungsten hexacarbonyl too, but it's not as, this asymmetry is not as large. So I'm just wondering what the mechanism of this is.
I don't know, but that's a good question. And so you can see it as clearly here, right? After we've subtracted out the reservoir, it's just like you say. It looks asymmetric. You get something on both sides with the UP, but only one side with the LP.
Yeah.
So we're going to ask the theorists if they can answer
that. All right, great. Well, I'm afraid we're over time. And yeah, I mean, I want to thank you, Jeff. This was a great presentation, and it looks like it sparked a whole lot of conversation, and hopefully this will keep going, and people will be able to contact you with all the questions, and you know, just try to make this thing grow even larger and be more productive. So well, with that, I just want to thank you again for being here, and let me remind you that next week we're going to have Wei Deng from the University of Michigan. So please tune in, same day, same time. I hope you stay safe, healthy, and well, just thank you for joining us in this initiative.
Thanks a lot, Jorge.
Good.